Hello there and welcome. Tonight we're going to drift down into the deepest, most peaceful corners of our planet. The vast underwater world that covers more than 70% of Earth's surface yet remains more mysterious than the far side of the moon. We'll explore the gentle rhythms of life in the abyss, the soothing patterns that play out in crushing darkness, and the quiet wonders that exist miles beneath the waves. Some of what we'll discover will feel like poetry written in living light. Others will remind us that even in Earth's most extreme places, life finds a way to not just survive, but to create beauty. Each fact will carry you deeper into a world where time moves differently, where silence has weight, and where the impossible becomes everyday reality. Tonight, we're going to let these ocean mysteries wash over you like a gentle current. You might find yourself drifting towards sleep, or perhaps simply floating in the background of these underwater revelations. If you enjoy these journeys into the hidden corners of our world, feel free to like and subscribe or share your thoughts in the comments below. But for now, all you need to do is settle in. Let your breathing slow to match the rhythm of deep ocean currents, and allow yourself to sink peacefully into the most relaxing deep sea discoveries science has to offer. Let's begin our descent. The deep ocean makes its own oxygen in complete darkness. Far below where sunlight has ever touched, scientists recently discovered something that changes everything we thought we knew about how life sustains itself. In the deepest trenches and abyssal plains where eternal night reigns supreme, the seafloor itself is quietly producing oxygen. Not through photosynthesis, which requires light, but through a process so remarkable that researchers are calling it dark oxygen production. Picture this vast underwater landscape carpeted with mysterious metallic nodules that have been growing for millions of years. These potato-shaped formations, scattered across the ocean floor like ancient artifacts, are somehow splitting water molecules and releasing breathable oxygen into the surrounding water. The process is so gentle, so constant, that it creates invisible streams of life, giving gas flowing through the darkness. Scientists measure this dark oxygen with delicate instruments, watching numbers climb steadily as these nodules work their quiet magic, supporting entire communities of deep sea life that should not exist in such an oxygen-poor environment. The discovery suggests that our planet's deepest waters are not the barren wasteland we once imagined, but rather a place where chemistry itself becomes a form of life support. These nodules, formed grain by grain over epochs we can barely comprehend, have been silently creating the conditions for life to flourish in Earth's most unlikely places. The oxygen they produce moves through the water like invisible breath, sustaining creatures that live their entire lives without ever knowing the touch of sunlight. This dark oxygen production happens on a scale that's both microscopic and massive. Each individual nodule contributes just a whisper of oxygen to the surrounding water, but multiplied across thousands of square kilometers of seafloor, the effect becomes substantial enough to support complex ecosystems. The process is so gentle and consistent that it creates a baseline of breathable water that has likely been supporting deep ocean life for millions of years, unnoticed by science until now. In the midnight zone, where no sunlight has ever penetrated, 80% of all creatures create their own light. This means that 4 out of every 5 animals living between 600 and 3,000 feet below the surface can produce bioluminescence, turning the deep ocean into nature's largest light show. The statistics are staggering when you consider that this represents millions upon millions of living beings. each one carrying the ability to paint the darkness with living color. Most of this underwater aurora appears as blue-green light, colors that can travel through water more effectively than any others. These shorter wavelengths slice through the liquid darkness like gentle laser beams, creating a communication network that spans the entire water column. While red light from the sun cannot reach these depths at all, the ocean has developed its own palette, one where blue and green become the languages of survival and beauty. Imagine floating in this bioluminescent realm, surrounded by countless tiny stars that pulse and flicker with purpose. Jellyfish drift by like living galaxies, their bell-shaped bodies outlined in ethereal blue light. Schools of lanternfish create moving constellations, each individual contributing a single point of light to patterns that shift and flow like slow-motion fireworks. Deep-sea squid pulse with waves of bioluminescence that ripple across their skin, while tiny plankton sparkle like underwater snow whenever disturbed by passing currents. This living light serves purposes both practical and mysterious. Some creatures use it to hunt, creating lures that draw curious prey close enough to capture. Others flash in patterns that serve as identification, helping them find their own species in the vast darkness. Still others use bioluminescence as camouflage, matching the faint, downwelling light from above to blend seamlessly with their surroundings. The result is a three-dimensional light show that never stops, never sleeps, and never fails to create moments of wonder for the few humans lucky enough to witness it. The famous anglerfish demonstrates one of the most elegant uses of bioluminescence in the deep sea. These patient hunters carry fishing rods made of modified spine tipped with glowing lures that contain millions of light-producing bacteria. The lure dangles in front of the anglerfish's massive jaws like a tiny beacon, pulsing gently in the darkness to attract curious prey. When a smaller fish approaches to investigate this mysterious light, the anglerfish can snap its jaws shut in milliseconds, capturing a meal in one of nature's most efficient traps. The bacteria that create this light have formed a partnership with their host that benefits both species. The anglerfish provides them with nutrients and a safe place to live, while the bacteria provide the anglerfish with a hunting tool that requires no energy beyond what's needed to keep them healthy. This symbiotic relationship has been perfected over millions of years, creating a living lighthouse that operates continuously in the deep ocean's eternal night. Marine snow falls through the deep ocean like the world's most gentle blizzard, carrying life from the surface to the deepest trenches. This continuous precipitation of organic matter creates a peaceful rhythm in the abyss, where particles drift downward in a slow-motion dance that can take weeks to complete. Unlike terrestrial snow that melts and disappears, marine snow grows larger as it falls, collecting other particles and forming increasingly substantial flakes that provide sustenance for creatures throughout the water column. Picture these organic snowflakes beginning their journey in the sunlit waters above, where microscopic plankton, fragments of seaweed, and the waste products of surface-dwelling creatures combine into tiny packages of nutrition. As they sink, these packages attract other particles, growing from specks barely visible to the naked eye into aggregations the size of coffee beans or even larger. The larger they become, the faster they fall, but even at their quickest descent, the journey to the ocean floor is measured in weeks rather than hours. This underwater snowfall provides the foundation for virtually all life in the deep sea. Since sunlight cannot penetrate to these depths, The organisms that live here depend entirely on this gentle rain of organic matter for their survival. The marine snow that reaches the sea floor creates a soft carpet of nutrients that supports bottom-dwelling creatures, while the snow that gets consumed along the way feeds the countless animals that live in the water column itself. 815 million tons of carbon reach the ocean floor every year through this process, making marine snow one of the most important carbon storage systems on our planet. As this organic matter settles into the sediment, it becomes buried and locked away from the atmosphere for thousands of years. In this way, the deep ocean serves as Earth's largest carbon vault, quietly storing away the building blocks of life in a process so gentle and continuous that it resembles meditation more than anything else. The journey of marine snow is remarkably peaceful to witness. In the deep sea, where currents are subtle and movements are slow, these organic particles drift downward like thoughts settling into sleep. They tumble and rotate gently, sometimes catching on the fins or tentacles of passing creatures, sometimes clustering together in temporary formations before continuing their descent. There is no urgency to this process, no violence or competition, just the steady, patient transfer of life from the bright surface world to the quiet depths below. Scientists studying marine snow often describe the experience as hypnotic. Watching through the cameras of deep-sea submersibles, they observe this continuous snowfall against the backdrop of absolute darkness, illuminated only by the artificial lights of their research vehicles. The particles appear and disappear at the edges of their vision like tiny ghosts, creating a sense of movement and life in places that seem utterly still. Some researchers report that watching marine snowfall can be so soothing that they find themselves becoming drowsy during long hours of deep-sea observation. The deep ocean experiences pressure that would crush the human body instantly, yet life thrives under conditions that seem impossible. At the average ocean depth of about 12,000 feet, the pressure is 380 times greater than what we experience at sea level. In the deepest trenches, this crushing force increases to over 1,000 times atmospheric pressure, creating an environment where the weight of water above presses down with the force of a mountain. To understand this incredible pressure, imagined meters depth, the force that at 2,000 pressing down on every square inch of surface area equals the weight of 500 fully grown Galapagos tortoises. At the deepest point in the ocean, nearly 11,000 meters down, this pressure would instantly collapse human lungs, rupture eardrums, and crush bones. The water itself becomes dense enough to affect the behavior of light and sound, creating an environment that operates according to physics most surface dwellers never experience. Yet in this crushing realm, life not only survives, but creates some of the most remarkable adaptations on Earth. Deep sea creatures have evolved bodies that are perfectly suited to these extreme conditions, with proteins and cellular structures that remain stable under pressures that would destroy surface-dwelling organisms. Some fish produce special compounds that counteract the crushing effects of deep water, while others have bodies that are mostly water themselves, eliminating the air spaces that would collapse under pressure. The most remarkable aspect of deep sea pressure adaptation is how peaceful it appears from the outside. These creatures don't struggle against the crushing force around them. Instead, they exist in perfect harmony with their high-pressure environment, moving with the same grace and efficiency as surface animals move through air. A deep sea fish gliding through water under crushing pressure appears as calm and effortless as a bird soaring through the sky, demonstrating that adaptation can create beauty even under the most extreme conditions. This pressure creates a world where the normal rules of physics take on new meaning. Sound travels differently in the deep ocean, often carrying farther than it would at the surface. Light behaves strangely, bending and refracting in ways that can create optical illusions for the creatures that live there. Even time seems to move differently as the intense pressure and eternal darkness create an environment where seasonal changes have no meaning, and the rhythm of life follows patterns established over millions of years. Giant tube worms cluster around hydrothermal vents in some of the most extraordinary ecosystems on Earth, creating underwater oases that support life densities 10,000 to 100,000 times greater than the surrounding sea floor. These remarkable creatures can grow up to 10 feet long and live their entire lives without mouths, stomachs, or digestive systems, instead relying on beneficial bacteria that live inside their bodies to convert chemicals from the vents into nutrients they can use. The tube worms themselves appear almost alien in their simplicity and elegance. Their bright red plumes extend from white tubes anchored to the rocky seafloor around the vents, creating underwater gardens that sway gently in the mineral-rich currents. These plumes contain specialized organs that absorb hydrogen sulfide and other chemicals from the vent water, passing them along to the billions of bacteria that live in the worm's body tissues. These hydrothermal vent ecosystems represent some of the fastest growing environments in the deep sea. Tube worms can add 33 inches to their length in a single year, making them among the most rapidly growing marine invertebrates known to science. Their growth is fueled entirely by chemosynthesis, the process by which bacteria convert chemical energy into biological energy, creating a food web that operates completely independently of sunlight. The vents themselves create a surreal underwater landscape where scalding water rich in minerals erupts from cracks in the sea floor, creating underwater geysers that can reach temperatures of over 700 degrees Fahrenheit. Yet just inches away from these scorching flows, the water returns to its normal, near-freezing temperature, creating sharp gradients that the vent animals have learned to navigate with remarkable precision. The communities that develop around these underwater hot springs create complex neighborhoods in the abyss. Ghostly white crabs scuttle across the mineral deposits, their shells bleached pale by the lack of sunlight, but their movements quick and purposeful as they navigate between the scalding vents and the frigid surrounding water. Pale shrimp swarm in dense clouds around the tube worm colonies, their bodies translucent enough to reveal the intricate workings of their internal organs as they filter nutrients from the chemically rich water. Perhaps most remarkably, scientists have discovered that these vent ecosystems extend far beneath the visible sea floor. Lifting the hardened lava formations around active vents reveals hidden cavities where entire communities of creatures live in complete darkness, connected to the surface vents through a network of underground passages. These subterranean highways allow young animals to travel from vent to vent without ever exposing themselves to the harsh open ocean, creating a hidden superhighway system in the deep sea that operates entirely out of sight. The discovery of life beneath the sea floor suggests that the deep ocean contains even more habitat than we previously imagined. These underground chambers may harbor species that never venture to the surface, creating isolated populations that have evolved in complete separation from the rest of the ocean. The thought of entire ecosystems existing in spaces so hidden that they require special equipment just to access adds another layer of mystery to the deep sea's already incredible complexity. When whales die and sink to the ocean floor, they create banquets that can last for decades. A single whale fall represents the equivalent of 1,000 years worth of marine snow concentrated into one location, providing a sudden windfall of nutrients to creatures that normally survive on the sparse pickings of the deep sea. These massive carcasses create complex ecosystems that progress through distinct stages, each supporting different communities of life as the whale's body slowly returns to the sea. The first visitors to a fresh whale fall are the mobile scavengers that can smell the bounty from miles away. Six-gill sharks glide in from the darkness like living submarines, their ancient forms perfectly adapted for scavenging in the deep ocean's food-scarce environment. Hagfish arrive in writhing masses, using their remarkable ability to produce slime as both defense and feeding aid as they burrow into the whale's flesh. These creatures can feed continuously for months, growing fat on the abundance that whale falls provide. As the soft tissues disappear, a new community moves in to exploit the remaining resources. Bone-eating worms with acid secretions bore into the whale's skeleton, breaking down the lipids trapped inside the massive bones. These specialized organisms can spend years slowly dissolving their way through whale bones, creating a honeycomb of tunnels that provide shelter for other creatures, while releasing nutrients that support entire food webs. The final stage of a whale fall can persist for decades as bacteria break down the remaining lipids in the bones, creating sulfur compounds that attract the same types of creatures found around hydrothermal vents. Tube worms, clams, and other chemosynthetic organisms colonize the whale skeleton, creating a miniature version of a vent community that can survive long after the whale's flesh has disappeared. These communities represent some of the longest-lasting ecosystems in the deep sea, providing stable habitat for rare species that might otherwise struggle to find suitable homes in the vast emptiness of the abyss. The spacing between whale falls across the ocean floor creates stepping stones of abundance in an otherwise nutrient-poor environment. Scientists estimate that these carcasses are distributed just close enough together that specialized whale fall species can spread from one to another, maintaining populations across vast distances of deep-sea desert. This network of temporary oases supports unique species found nowhere else on Earth, creatures so adapted to the whale fall lifestyle that they cannot survive in any other environment. Kelp forests create underwater cathedrals that rival any terrestrial woodland in their beauty and complexity. These towering seaweeds can grow 18 inches in a single day under ideal conditions, reaching heights of 150 feet as they stretch toward the surface light. The growth rate of these marine plants is so rapid that entire forests can establish themselves in areas where none existed just months before, creating habitat for thousands of species with remarkable speed. Standing at the base of a kelp forest feels like entering a natural cathedral. The massive fronds create a canopy overhead that filters the sunlight into dancing patterns of green and gold, while the water between the kelp stalks moves with the gentle rhythm of ocean swells. Schools of fish weave between the kelp blades like flocks of birds navigating through tree branches, while sea otters float on their backs among the canopy, using the kelp as anchor points while they rest and groom. The three-dimensional structure of kelp forests provides habitat at every level, from the hold-fast roots that anchor to rocky bottoms to the gas-filled bladders that keep the fronds floating near the surface. Colorful anemones and sponges encrust the lower portions of the kelp stalks, while fish seek shelter among the middle reaches and seabirds dive from above to hunt in the upper canopy. This vertical stratification creates multiple distinct communities within a single forest, each adapted to different light levels and water conditions. Kelp forests serve as nurseries for countless marine species, providing protected spaces where young animals can grow to maturity before venturing into the open ocean. The complex structure of the forest breaks up wave action and creates calmer areas where small fish can find refuge from predators. The constant shedding of kelp fragments provides food for filter feeders and detritus eaters, while the living kelp supports grazing animals that browse on its surface like underwater deer. These underwater forests also play a crucial role in absorbing carbon dioxide from the atmosphere. As the kelp grows, it incorporates carbon into its tissues, and when fronds break away and sink to the seafloor, they carry this stored carbon down to the sediment where it can remain buried for centuries. This natural carbon sequestration process makes kelp forests important allies in the fight against climate change, quietly removing greenhouse gases from the atmosphere while creating some of the ocean's most productive ecosystems. The ocean's twilight zone represents the largest living space on our planet, yet it remains one of the most mysterious regions of Earth. This vast middle layer of the sea, stretching from 600 to 3,000 feet below the surface, contains more water than all other ocean zones combined, creating a three-dimensional habitat of almost incomprehensible size. No sunlight penetrates to these depths, yet the zone teems with life that has adapted to exist in perpetual darkness. Every night, the twilight zone participates in the largest migration on Earth as billions of creatures rise toward the surface to feed under cover of darkness. This daily vertical migration involves more biomass than any other regular movement of life on the planet, as lanternfish, squid, shrimp, and countless other species travel hundreds of feet upward to reach the productive surface waters where they can find food. As dawn approaches, this vast army of creatures descends back to the safety of the deep, carrying nutrients and carbon with them in a process that helps regulate our planet's climate. The sheer scale of this migration is difficult to comprehend. Military sonar operators first discovered the phenomenon during World War II, when they detected what appeared to be a false seafloor that moved up and down with the daily cycle. This deep scattering layer, as it became known, is actually composed of millions of swim bladders and gas-filled organs that reflect sound waves, creating an acoustic signature visible to sonar equipment from hundreds of miles away. The creatures that make this journey have evolved remarkable adaptations for life in the twilight zone's unique environment. Many species have large eyes to capture the faintest traces of light that filter down from above, while others have abandoned vision entirely and rely on other senses to navigate their dark world. Some have developed transparent bodies that make them nearly invisible to predators, while others use bioluminescence to create complex light displays for communication and hunting. The twilight zone's role in Earth's carbon cycle cannot be overstated. The creatures that migrate between the surface and the deep transport an estimated 2 to 6 billion tons of carbon annually into the deep ocean, effectively removing it from the atmosphere for centuries or millennia. This biological carbon pump helps regulate our planet's climate by storing greenhouse gases in the deep sea, making the twilight zone one of the most important climate regulation systems on Earth. Recent discoveries in the twilight zone continue to reveal its importance to ocean ecosystems. Scientists have found that bacteria in this region are iron-limited, producing special molecules to scavenge trace amounts of this essential nutrient from the surrounding water. These bacteria play crucial roles in breaking down organic matter as it sinks through the twilight zone, controlling the efficiency of the biological carbon pump and influencing how much carbon ultimately gets stored in the deep ocean. The discovery of new species in the deep ocean continues at a breathtaking pace, with every expedition revealing forms of life that seem more like products of imagination than evolution. In recent years, scientists have identified 866 new marine species, each one adding another brushstroke to the vast portrait of deep-sea biodiversity. These discoveries span depths from just beneath the surface to nearly 5,000 meters down, creating a catalog of life that grows more extraordinary with each edition. Among these newly discovered creatures are animals so unusual that they challenge our understanding of what life can become. Deep-sea corals that grow like underwater bonsai trees, their branches reaching into the current to filter nutrients from the passing water. Glass sponges that build elaborate scaffolding from silica, creating structures so delicate they seem like they might shatter at the slightest touch, yet strong enough to withstand the crushing pressure of the deep ocean. Squat lobsters with shells covered in spikes navigate the seafloor like tiny armored vehicles, their beady eyes scanning the darkness for food and threats. Cactus urchins, of which only one species was previously known, now reveal themselves to be part of a larger family of spiny wanderers that roll across the abyssal plains like tumbleweeds in an underwater desert. Each discovery adds another piece to the puzzle of deep sea life, revealing patterns and relationships that scientists are only beginning to understand. The translucent glass squid represent some of the most ethereal creatures in the deep ocean, their bodies so transparent that they seem like living windows into the water around them. These ghostly cephalopods drift through the twilight zone with movements so fluid they appear to be swimming through liquid air rather than water. Their transparency serves as perfect camouflage, making them nearly invisible to both predators and prey as they navigate the dim waters where the last traces of sunlight fade into absolute darkness. Perhaps most remarkably, researchers have witnessed fish using their fins like hands to walk across the sea floor, their bright red bodies standing out against the pale sediment like flowers blooming in a monochrome garden. These bottom walkers have evolved a completely different approach to life in the deep sea, abandoning the typical fish lifestyle of swimming through the water column in favor of a more deliberate existence exploring every crevice and hiding place on the ocean floor. The interconnected nature of deep-sea ecosystems becomes more apparent with each new discovery. Creatures that seem wildly different from one another often depend on each other in subtle ways, creating webs of relationship that span vast distances and connect habitats that appear completely separate. The bright corals that grow on underwater mountains provide shelter for the glass squid, while the walking fish stir up sediment that feeds the filter-feeding sponges, which in turn provide nutrients for the bacteria that support the entire food web. The deep ocean operates on temporal scales that dwarf human experience, creating an environment where patience becomes a survival strategy. In these depths, where temperature remains constant year-round and seasonal changes have no meaning, life unfolds according to rhythms measured in decades rather than days. Ancient corals grow so slowly that individual colonies can persist for thousands of years, becoming living libraries that record centuries of ocean conditions in their calcium carbonate skeletons. This temporal stability creates opportunities for relationships to develop that would be impossible in the rapidly changing surface world. Deep-sea creatures often form partnerships that last for entire lifetimes, with some species spending decades in close association with the same individuals. Cleaning stations on underwater mountains become meeting places where different species gather for mutual benefit, creating communities that persist for generations, with membership passed down from parents to offspring. The slow pace of deep sea life extends to reproduction as well, with many species investing years in producing just a few offspring. Deep sea fish often carry their eggs for months before releasing them, ensuring that each young animal has the best possible chance of survival in the food-scarce environment. Some species produce larvae that spend years drifting through the water column before settling into their adult habitat, a journey so long that the ocean conditions they experience as adults may be completely different from those they knew as juveniles. The rhythm of deep-sea currents provides a heartbeat for this underwater world, moving water and nutrients across ocean basins in cycles that take centuries to complete. These currents are so slow and gentle that they barely disturb the delicate creatures they encounter, creating a transportation system that allows deep-sea animals to travel vast distances without effort. Jellyfish and other drifting creatures ride these currents like passengers on an extremely slow train, covering thousands of miles over the course of their lifetimes. The deep ocean's role as Earth's climate regulator becomes more impressive when viewed from the perspective of geological time. The carbon that gets buried in deep-sea sediments today will remain locked away from the atmosphere for periods that span multiple ice ages. This makes the deep ocean a crucial buffer against rapid climate change. Storing away the excess carbon dioxide from human activities in sediments that will not release their contents back to the atmosphere for thousands of years. The thermohaline circulation that drives deep ocean currents operates like a massive conveyor belt, carrying water from the surface to the depths and back again in a cycle that takes more than 1,000 years to complete. This circulation system means that some of the water in the deepest trenches last saw sunlight when medieval cathedrals were being built, creating a connection between the deep sea and human history that spans centuries. Scientists studying deep sea sediments can read the history of our planet's climate like pages in a book, with each layer of accumulated marine snow recording the conditions that existed when it was deposited. Ice ages and warm periods, volcanic eruptions, and meteor impacts all leave their signatures in the deep sea sediments, creating an archive of Earth's history that stretches back millions of years. The stability of deep sea temperatures creates an environment where chemical processes can proceed at rates that remain constant for millennia. This consistency allows deep sea creatures to fine-tune their metabolisms to operate at maximum efficiency, creating some of the most energy-conscious lifestyles on Earth. Many deep-sea animals have metabolic rates so slow that they can survive for months without eating, waiting patiently for the next meal to drift within range. The deep ocean's darkness eliminates the daily rhythm that governs most life on Earth, creating an environment where time becomes fluid and flexible. Without the rising and setting of the sun to mark the passage of days, deep sea creatures develop their own internal rhythms based on food availability, reproductive cycles, and the subtle variations in current patterns that provide the only temporal markers in their world. This temporal freedom allows deep-sea animals to optimize their activities around opportunities rather than schedules. When food becomes available, they can feed continuously for days or weeks. When conditions are poor, they can enter states of suspended animation that allow them to wait out difficult periods without depleting their energy reserves. This flexibility makes deep-sea creatures remarkably resilient to environmental changes, able to adapt their behavior to match whatever conditions they encounter. The bioluminescent displays that light up the deep ocean operate on their own temporal rhythms, with different species timing their light shows to avoid interference from each other. Some creatures flash in rapid bursts that last only milliseconds, while others produce steady glows that continue for hours. The result is a coordinated light show that changes constantly but never becomes chaotic, as each species contributes its own signature to the overall display. The chemical signals that deep-sea creatures use for communication can persist in the water for hours or even days, creating invisible message networks that span vast areas of ocean. These chemical trails allow animals to communicate across distances that would make visual or acoustic signals impossible, creating communities that extend far beyond what any individual creature can see or hear. The deep ocean's crushing pressure creates unique opportunities for life to explore biochemical solutions that would be impossible at the surface. Proteins that would unfold and become useless in low-pressure environments remain stable and functional under the extreme conditions of the deep sea, allowing deep-sea creatures to develop metabolic pathways that operate according to different rules than surface life. The density of deep ocean water affects the way sound travels, creating acoustic environments that seem to follow different laws of physics. Whale songs can travel for hundreds of miles through the deep ocean, creating communication networks that span entire ocean basins. The calls of deep-sea creatures blend into a subtle symphony that plays continuously in the abyss, a soundtrack to life in Earth's most remote habitat. The magnetic properties of deep-sea sediments create navigation aids that some creatures may use to find their way across the featureless abyssal plains. These magnetic signatures change gradually over vast distances, providing a kind of underwater GPS system that allows deep-sea animals to maintain their sense of direction even in complete darkness. The deep ocean's remoteness from human activity creates one of the few remaining places on Earth where natural processes can unfold without interference. This isolation allows deep-sea ecosystems to operate according to principles that have remained unchanged for millions of years, providing scientists with glimpses of how Earth systems functioned before human influence began to alter the planet's natural cycles. The vast scale of the deep ocean means that even dramatic events can unfold in relative solitude, with underwater avalanches, volcanic eruptions, and massive storms occurring in regions so remote that they leave no trace in human awareness. These hidden dramas play out according to their own rules, creating landscapes and seascapes that exist in a state of constant but imperceptible change. The deep ocean represents the largest repository of liquid water in the solar system, containing more than 97% of all the water on Earth. This vast reservoir serves as a buffer against changes in sea level, temperature, and chemical composition, absorbing variations that would otherwise create dramatic swings in Earth's climate. The sheer volume of water in the deep ocean means that it can absorb enormous amounts of heat and carbon dioxide without showing significant changes in temperature or chemistry. The pressure gradients that exist in the deep ocean create opportunities for unique forms of life that exist nowhere else in the known universe. These pressure-adapted organisms represent evolutionary solutions to problems that most life forms never encounter, demonstrating the remarkable creativity of biological systems when faced with extreme conditions. Their existence expands our understanding of the possible forms that life can take, suggesting that similar creatures might exist in the high-pressure environments of other planets and moons. The deep ocean's role as a planetary thermostat becomes more crucial as climate change accelerates, with the deep sea serving as both a sink for excess heat and carbon dioxide and a source of stability that helps moderate the rate of environmental change. The thermal inertia of deep ocean water means that temperatures in the abyss change very slowly, providing a stable foundation that helps prevent runaway climate shifts that could make the planet uninhabitable. The cycling of nutrients between the surface and the deep ocean creates a planetary circulation system that has operated continuously for billions of years, connecting every part of Earth's biosphere in an intricate web of chemical and biological relationships. This global circulation ensures that essential elements remain available to life throughout the planet, preventing any single region from becoming permanently depleted of the nutrients needed to support complex ecosystems. The deep ocean's hidden valleys and underwater mountain ranges create landscapes more dramatic than anything found on land. Yet most of these geological wonders remain unmapped and unexplored. Massive underwater canyons stretch for hundreds of miles across the abyssal plains, their walls dropping thousands of feet into trenches so deep they could swallow entire mountain ranges. These submarine valleys were carved by ancient currents and underwater avalanches over millions of years, creating corridors that channel deep water flows and serve as highways for migrating deep sea creatures. The Mid-Atlantic Ridge runs like a spine down the center of the Atlantic Ocean, a volcanic mountain chain that rises more than 10,000 feet from the surrounding sea floor, yet remains completely hidden beneath miles of water. Along this ridge, new ocean floor is born as molten rock erupts from the Earth's interior, creating underwater landscapes that are younger than some of the trees growing on land. The ridge system extends for 40,000 miles around the globe, making it the longest mountain range on Earth, yet few people know of its existence. Seamounts dot the deep ocean like underwater islands, isolated peaks that rise from the abyssal depths, habitats for creatures that spec to create unique habitats in living on hard surfaces. These underwater mountains often support their own endemic species, creatures found nowhere else on Earth that have evolved in isolation on their rocky ends that flow around summits. The curved seamounts create upwelling that brings nutrients from the deep, turning these underwater peaks into oases of abundance in the otherwise sparse deep sea. The flattest places on Earth exist on the abyssal plains, vast stretches of deep sea floor that extend for thousands of miles, with slopes so gentle they're measured in inches per mile rather than feet. These underwater prairies are covered in fine sediment that has been accumulating for millions of years, creating surfaces so level they make terrestrial plains look mountainous by comparison. The monotony of these landscapes is broken only by the occasional whale fall or the tracks left by deep sea creatures as they wander across the sediment in search of food. Underwater waterfalls cascade down the continental slopes where dense, cold water flows beneath warmer water masses, creating invisible rivers that can be hundreds of times larger than the Amazon. These submarine cataracts flow with such power that they carve channels in the sea floor. yet they remain completely hidden from surface observation. The Denmark Strait cataract between Greenland and Iceland carries more water than all the rivers on land combined, plunging 3 miles down the underwater mountainside in a flow that continues year-round. The deep ocean's trenches represent the most extreme environments on our planet, places where the seafloor plunges to depths that exceed the height of Mount Everest. The Mariana Trench, the deepest known part of Earth's surface, descends more than 36,000 feet below sea level, creating a chasm so deep that if Mount Everest were placed at its bottom, the peak would still be more than a mile underwater. The pressure at these depths exceeds 1,000 times atmospheric pressure, yet life persists even in these most crushing environments. These trenches form where oceanic plates collide and one slides beneath the other, creating subduction zones that swallow seafloor at rates measured in inches per year. The process is so slow and steady that it creates remarkably stable environments despite the incredible geological forces at work. Creatures living in these trenches experience conditions that remain virtually unchanged for thousands of years, creating opportunities for highly specialized adaptations to evolve. The walls of deep ocean trenches are often covered with bacterial mats that create living carpets across the rocky surfaces. These microbial communities survive by processing chemicals that seep from the Earth's interior, creating food webs that operate entirely independently of sunlight. The bacteria form colorful patches that can be seen from submersibles, painting the trench walls in shades of orange, white, and purple that provide the only color in an otherwise monochrome environment. Strange fish adapted to the extreme pressure of the trenches have bodies that appear almost gelatinous, with bones so soft they bend like cartilage, and organs that are specially modified to function under crushing pressure. These deepest dwelling vertebrates move with slow, deliberate motions that conserve energy in an environment where food is extraordinarily scarce. Some species have evolved to feed exclusively on organic matter that rains down from above, positioning themselves like living rain gauges to catch whatever nutrition happens to fall within their reach. The Hadal Zone, named after Greek under Hades, the ancient world, encompasses all ocean depths greater than 20,000 feet. This realm represents less than 2% of the ocean by area, yet it contains some of the most unique life forms on Earth. Creatures in the Hadal Zone have evolved solutions to survival problems that exist nowhere else, creating biological innovations that push the boundaries of what we thought life could achieve. The sediment in deep ocean trenches often contains layers that record major events in Earth's history, with each stratum telling the story of meteor impacts, ice ages, and massive volcanic eruptions. These geological archives preserve evidence of planetary catastrophes that occurred millions of years ago, creating libraries of Earth's history that scientists can read by analyzing the chemical composition of different sediment layers. The isolation of deep ocean trenches creates opportunities for evolution to proceed along completely separate paths, resulting in species that have no close relatives anywhere else on the planet. Some trench-dwelling creatures appear to be living fossils, representing evolutionary lineages that disappeared from other environments millions of years ago, but persisted in the stable conditions of the deep trenches. The temperature at the bottom of the deepest trenches remains just above freezing year-round, creating environments where the seasons have no meaning and the passage of time is marked only by the slow accumulation of sediment and the even slower processes of geological change. This thermal stability allows chemical reactions to proceed at consistent rates, creating predictable environmental conditions that support highly specialized ecosystems. The sound environment in deep ocean trenches is dominated by the creaking and groaning of the Earth's crust as tectonic plates slowly grind against each other. These geological sounds create a constant low-frequency rumble that provides an acoustic backdrop to life in the trenches, a planetary heartbeat that has continued unchanged for millions of years. Deep-sea mining operations threaten to disrupt ecosystems that took millions of years to develop, potentially destroying communities of creatures before scientists have a chance to study them. The polymetallic nodules that carpet parts of the deep-sea floor represent both valuable mineral resources and crucial habitat for deep-sea life. These potato-sized formations grow so slowly that individual nodules may be older than complex life on Earth, yet they could be harvested in a matter of years. The creatures that live on and around these nodules have evolved to depend on the specific chemical and physical properties of these formations. Some organisms use the nodules as attachment points in an environment where hard surfaces are rare to process, while others have evolved the metals contained within the nodules as part of their metabolic processes. The removal of these formations would eliminate habitat that cannot be replaced on any human timescale. The sediment plumes created by deep-sea mining operations could smother filter-feeding creatures across vast areas of the sea floor, disrupting food webs that extend throughout the water column. The fine particles stirred up by mining equipment would remain suspended in the deep ocean for months or years, creating clouds of sediment that could interfere with the feeding and reproduction of countless species. The slow growth rates and long lifespans of deep-sea creatures mean that populations damaged by mining activities could take centuries to recover, if they recover at all. Many deep-sea species reproduce only once in their lifetimes and have such low population densities that finding mates is already a significant challenge. Any reduction in population size could push these species beyond the point where sustainable reproduction is possible. The deep ocean's role in regulating Earth's climate makes the protection of deep-sea ecosystems crucial for planetary stability. The organisms that live in the deep sea play essential roles in carbon cycling, nutrient distribution, and the maintenance of ocean chemistry. Disrupting these systems could have consequences that extend far beyond the immediate area of mining operations, potentially affecting global climate patterns and ocean productivity. The vastness of the deep ocean creates a sense of perspective that can be both humbling and comforting. In a world where human activity has altered nearly every terrestrial landscape, the deep sea remains largely unchanged, operating according to natural principles that have persisted for millions of years. This continuity provides a reminder that some processes are larger than human influence, that there are still places where nature follows its own rhythm without interruption. The exploration of the deep ocean continues to reveal the remarkable diversity and resilience of life on our planet. Each expedition into the abyss brings back images and specimens that expand our understanding of what life can achieve under extreme conditions. These discoveries not only satisfy human curiosity about the unknown, but also provide insights into the fundamental processes that sustain life throughout the universe. The deep ocean represents the largest unexplored frontier remaining on Earth, a three-dimensional wilderness that contains more unknown territory than all the continents combined. The fact that we know more about the surface of Mars than about our own deep sea demonstrates how much mystery still surrounds us, how much wonder remains to be discovered in the depths of our own planet. The technology required to explore the deep ocean continues to advance, bringing previously inaccessible regions within reach of human observation. Autonomous underwater vehicles can now spend months in the deep sea, following migrating creatures and monitoring changes in deep-sea ecosystems with unprecedented detail. These robotic explorers serve as our ambassadors to the abyss, bringing back data and imagery that reveal the hidden lives of deep-sea creatures. The bioluminescent communications that flash through the deep ocean create a language of light that we are only beginning to understand. Each species appears to have its own vocabulary of flashes, pulses, and glows that convey information about identity, location, and intent. The complexity of these light-based conversations suggests that the deep sea is far from the silent, empty place it was once thought to be. The partnership species in the deep ocean demonstrate between different the power of cooperation in extreme environments. Creatures that might compete for resources in more abundant habitats instead form alliances that benefit all parties involved. These symbiotic relationships create networks of mutual support that span multiple species and extend across vast areas of the deep sea floor. The seasonal migrations that connect surface and deep ocean communities create vertical highways that transport nutrients, energy, and genetic material between different layers of the sea. These daily and seasonal movements of billions of creatures represent some of the largest biological phenomena on Earth, yet they occur largely out of sight beneath the waves. The chemical signatures that deep sea creatures leave in the water create invisible trails that can persist for days, allowing animals to communicate across distances that would make other forms of contact impossible. These molecular messages carry information about species identity, reproductive status, and territorial boundaries, creating a chemical communication network that spans the entire deep ocean. The deep sea's connection to surface waters through currents and migrations means that changes in the abyss can affect marine ecosystems throughout the water column. The health of deep-sea communities influences the productivity of surface waters, the abundance of commercially important fish species, and the ocean's capacity to absorb carbon dioxide from the atmosphere. The preservation of deep-sea habitats requires international cooperation on a scale that matches the global nature of ocean ecosystems. The deep sea recognizes no national boundaries, and the creatures that live there migrate freely across political divisions that exist only on human maps. Protecting these environments requires agreements that transcend individual national interests and embrace the shared responsibility for maintaining planetary systems. The study of deep-sea ecosystems provides insights into the resilience and adaptability of life that could prove crucial as our planet faces rapid environmental change. The creatures that thrive in the extreme conditions of the deep ocean demonstrate survival strategies that could inform efforts to help other species adapt to changing conditions on land and in surface waters. The deep ocean's role as a reservoir of biodiversity becomes more important as climate change and human activities reduce the diversity of life in other environments. The species that have evolved in the deep sea represent millions of years of evolutionary experimentation, creating a genetic library that could prove invaluable for understanding life's potential and developing new approaches to biotechnology and medicine. The minerals and compounds produced by deep-sea creatures continue to yield new discoveries with applications in human medicine, materials science, and biotechnology. The unique chemical solutions that deep-sea organisms have evolved to survive in extreme conditions often have properties that could be useful in industrial applications or therapeutic treatments. The deep ocean's vast scale and three-dimensional complexity create opportunities our understanding of life on for discoveries that could reshape Earth. Every expedition into the abyss reveals new species, new behaviors, and new ecological relationships that add pieces to the puzzle of how life organizes itself in extreme environments. The rhythms of deep sea life provide a counterpoint to the accelerating pace of change on land and in surface waters. The slow, steady processes that govern deep-sea ecosystems offer a model of sustainability that has persisted for millions of years, demonstrating that complex systems can maintain stability over geological timescales. The silence and darkness of the deep ocean create an environment where subtle signals become amplified and minor variations take on major significance. In this realm of minimal stimulation, the smallest bioluminescent flash or chemical trace can convey crucial information, creating a world where whispers carry the weight of shouts. The deep ocean's influence on global weather patterns extends far beyond the marine environment, affecting rainfall, temperature, and storm patterns around the world. The heat absorbed by deep ocean waters helps moderate climate extremes, while the circulation patterns that move this water around the globe help distribute thermal energy from the equator toward the poles. The deep sea serves as a vast library of Earth's climate history, with sediment cores revealing detailed records of past environmental conditions that help scientists understand natural climate variability and predict future changes. This geological memory provides context for current climate trends and helps distinguish between natural variations and human-induced changes. The creatures of the deep ocean have evolved solutions to problems that exist nowhere else on Earth, creating biological innovations that expand our understanding of life's possibilities. These adaptations represent millions of years of evolutionary research and development, producing technologies that human engineers are only beginning to understand and appreciate. The deep ocean's capacity to inspire wonder and humility remains one of its most important gifts to humanity. In an age when human influence extends to every corner of the planet, the deep sea provides a reminder of the vastness and complexity of the natural world, encouraging the kind of perspective that comes from recognizing our place within larger systems. The future exploration of the deep ocean promises to reveal even more remarkable discoveries as technology advances and our ability to observe and interact with deep sea environments improves. Each new tool for studying the abyss opens previously hidden aspects of deep sea life to human observation, expanding our awareness of the complexity and beauty that exists in Earth's most remote habitats. The deep ocean's relationship with time reveals itself in ways that challenge our surface-dwelling understanding of how life unfolds. In these crushing depths, where the sun has never penetrated, creatures have evolved to exist in a state of temporal meditation, their lives unfolding according to rhythms that span decades rather than seasons. The ancient deep-sea corals that build their calcium carbonate skeletons one microscopic layer at a time create living monuments that record centuries of ocean chemistry in their slowly growing branches. These coral gardens of the abyss grow so gradually that individual colonies become archives of environmental history. their skeletal bands marking years like tree rings, but at a pace that makes terrestrial growth seem frantic by comparison. Some of these deep-sea corals are thousands of years old, meaning they began their patient construction when human civilizations were just learning to work metal, and they continue their slow building today, adding layer upon microscopic layer with the persistence of geological processes. The fish that swim among these ancient coral formations move with the unhurried grace of creatures that have learned to conserve every calorie in an environment where the next meal might be weeks away. Their movements appear almost choreographed, each motion calculated to achieve maximum efficiency with minimum energy expenditure. These deep-sea swimmers have metabolism so finely tuned to their environment that they can survive for months without feeding, entering states of near suspension that allow them to wait patiently for opportunity to present itself. The bacterial communities that carpet the deep sea floor operate on chemical cycles that unfold over years rather than days, processing nutrients so slowly that their metabolic rhythms become almost geological in their pace. These microbial mats create colorful patterns across the sediment that change imperceptibly over time, like living paintings that reveal their artistry only to observers patient enough to watch their slow transformation. The bacteria themselves represent some of the most ancient forms of life on Earth. Their basic cellular machinery virtually unchanged from ancestors that lived billions of years ago. The current systems that flow through the deep ocean move with the inevitability of continental drift, carrying water masses on journeys that span entire ocean basins over the course of centuries. These deep currents are so vast and persistent that they create their own geography, carving channels in the sea floor and depositing sediments in patterns that reflect current flows from thousands of years past. The water itself becomes a kind of time machine, carrying dissolved chemicals and microscopic life forms on voyages that connect the deepest trenches with distant polar seas. The reproductive cycles of deep sea creatures reflect the temporal luxury of life in a stable environment, with many species taking years to reach sexual maturity and investing enormous energy in producing just a few offspring. Deep sea squid carry their eggs for months, protecting them in specialized pouches, while the embryos develop with the thoroughness that only unlimited time can provide. The resulting juveniles emerge fully formed and equipped for life in the abyss, their development complete in ways that eliminate the vulnerable larval stages common in surface-dwelling species. The chemical communications that pass between deep-sea organisms create invisible networks that persist in the water for days or weeks, allowing creatures separated by vast distances to exchange information about food sources, territorial boundaries, and reproductive availability. These molecular messages drift through the water like underwater pheromone trails, creating a chemical landscape that changes slowly enough for deep-sea animals to navigate by scent across distances that would make visual contact impossible. The bioluminescent displays that punctuate the darkness of the deep sea follow temporal patterns that reflect the unique sensory environment of the abyss. Without the daily cycle of sunlight to provide temporal reference points, deep sea creatures have developed their own circadian rhythms based on food availability, predator activity, and the subtle chemical changes that mark the passage of time in the deep ocean. These biological clocks operate independently of surface time, creating communities that march to the beat of an underwater drummer whose rhythm is set by processes that exist only in the deep. The feeding relationships in deep-sea communities unfold with the patience of creatures that cannot afford to waste energy on unsuccessful hunting attempts. Predators in the deep sea often spend hours positioning themselves for a single strike, waiting motionless in the water column until prey ventures within range. These hunting strategies reflect an understanding that in the deep ocean, patience is not just a virtue but a survival requirement. The energy cost of movement in the crushing deep-sea environment means that every action must be calculated to provide a net energy gain. The symbiotic relationships that develop between deep-sea species often last for the entire lifetimes of the participating organisms, creating partnerships that span decades and involve multiple generations of smaller species living in association with longer-lived hosts. Deep sea sponges provide homes for entire communities of small creatures, their complex internal structures creating apartment buildings in the abyss that house dozens of species in carefully organized neighborhoods. These living cities grow slowly but persistently, adding new chambers and corridors over the years as their populations expand and diversify. The geological processes that shape the deep sea floor operate on timescales that make even the longest-lived deep-sea creatures seem ephemeral by comparison. Underwater mountain ranges rise grain by grain as tectonic forces slowly push oceanic crust upward, creating new habitat for deep-sea communities over periods measured in millions of years. The volcanic activity that shapes these underwater landscapes follows cycles that span millennia, with individual vents remaining active for centuries before cooling and being replaced by new eruptions elsewhere along the ridge systems. The sediment layers that accumulate on the deep sea floor create stratigraphic records that preserve the history of ocean chemistry, climate change, and biological productivity over periods that encompass the entire history of complex life on Earth. Each microscopic layer represents a snapshot of ocean conditions from a specific moment in the past, with the thickness and composition of the layers reflecting everything from volcanic eruptions to ice ages to mass extinction events. These sedimentary archives provide scientists with detailed records of how Earth's ocean systems have responded to environmental changes over geological time. The evolution of deep-sea species proceeds along pathways that reflect the unique selective pressures of life in the abyss, with environmental stability allowing for the development of highly specialized adaptations that would be impossible in more variable habitats. The extreme conditions of the deep sea create opportunities for evolutionary experimentation that can persist for millions of years, resulting in creatures that represent successful solutions to survival problems that exist nowhere else on Earth. These deep sea specialists often have no close relatives in surface waters, their evolutionary lineages having diverged so long ago that they represent entire families of organisms found only in the depths. The migration patterns that connect different regions of the deep sea create superhighways for genetic exchange that operate over distances spanning entire ocean basins. Deep sea creatures that appear sedentary often participate in complex life cycles that involve larval stages capable of traveling thousands of miles on deep ocean currents, creating genetic connections between populations separated by vast distances. These underwater migration routes have remained stable for thousands of years, creating reliable pathways that allow deep sea species to maintain genetic diversity across their enormous ranges. The energy budgets of deep sea ecosystems reflect the fundamental constraint of life in a food-limited environment, with every calorie carefully allocated between growth, reproduction, and survival activities. Deep sea creatures have evolved metabolic efficiencies that surpass anything found in surface waters. Their cellular machinery fine-tuned to extract maximum energy from minimal food inputs. These energy conservation strategies create communities where waste is virtually unknown, with every scrap of organic matter recycled through multiple levels of the food web before finally being incorporated into the sediment. The social structures that develop among deep-sea species often reflect the challenges of finding mates and maintaining territories in an environment where encounters between individuals may be separated by months or years. Some deep-sea fish have evolved elaborate courtship rituals that can be detected across vast distances, using bioluminescent displays and chemical signals to advertise their presence to potential mates swimming in the darkness miles away. These long-distance relationships require patience and persistence that would be impossible for surface-dwelling species operating under the time pressures of daily and seasonal cycles. The acoustic environment of the deep sea creates opportunities for communication and navigation that take advantage of the unique sound transmission properties of high-pressure water. Whale songs can travel for hundreds of miles through the deep ocean, creating communication networks that span entire ocean basins and allow individual whales to maintain contact with their social groups across distances that would make visual or chemical communication impossible. The deep sea's acoustic properties also allow smaller creatures to use sound for echolocation and prey detection with precision that rivals the most sophisticated sonar systems. The chemical gradients that exist in deep sea environments create three-dimensional landscapes of taste and smell that deep sea creatures navigate with the skill of sommeliers distinguishing between vintage wines. The ability to detect minute differences in water chemistry allows deep sea animals to locate food sources, identify territorial boundaries, and find suitable mates in an environment where visual cues are limited or non-existent. These chemical navigation systems operate continuously, creating sensory maps of the deep sea that are constantly updated as water masses move and mix. The pressure adaptations that allow deep sea creatures to survive in crushing environments create biological solutions that seem to defy the laws of physics as we understand them at surface pressures. Deep sea proteins maintain their functional shapes under conditions that would instantly denature surface proteins, while deep sea cell membranes remain flexible and permeable despite pressures that would collapse surface cell structures. These molecular adaptations represent millions of years of evolutionary fine-tuning, creating biological machinery that operates according to different rules than surface life. The reproductive strategies of deep-sea species often involve elaborate adaptations that ensure successful mating, despite the challenges of finding partners in the vast darkness of the abyss. Some deep-sea anglerfish have evolved systems where tiny males permanently fuse with much larger females, creating hermaphroditic partnerships that guarantee reproductive success without the need to search for mates in the enormous deep ocean. These biological solutions to the problems of deep-sea reproduction demonstrate the remarkable creativity of evolutionary processes when faced with extreme environmental constraints. The feeding adaptations of deep-sea creatures reflect the reality of life in an environment where meals are infrequent and must be maximized when they occur. Deep-sea fish often have expandable stomachs that allow them to consume prey larger than themselves, while their jaw structures are designed to prevent any captured food from escaping. These anatomical modifications create creatures that appear almost mythical in their proportions, with massive mouths and distensible bodies that can accommodate prey encounters ranging from tiny copepods to fish nearly as large as the predator itself. The camouflage strategies employed by deep-sea creatures take advantage of the unique optical properties of the deep ocean environment, where bioluminescence provides the primary source of illumination. Counter-illumination camouflage allows deep-sea animals to match the faint, downwelling light from above, making them invisible to predators looking up from below. This sophisticated camouflage system requires precise control of bioluminescent organs and real-time adjustment to changing light conditions, creating camouflage systems that surpass anything developed by human technology. The territorial behaviors of deep-sea species often involve the defense of resources that may seem insignificant to surface observers, but represent crucial survival advantages in the resource-limited deep ocean. Individual rocks or coral formations may be defended by generations of the same species, with territorial boundaries passed down through learned behaviors that persist long after the original territory holders have died. These underwater real estate markets operate according to rules that reflect the scarcity and value of suitable habitat in the deep sea environment. The seasonal patterns that exist in the deep sea are driven not by sunlight cycles, but by the rain of organic matter that falls from productive surface waters during specific times of year. These seasonal pulses of food create boom and bust cycles in deep sea communities, with periods of abundance followed by months of scarcity that test the survival skills of deep sea organisms. The ability to predict and prepare for these seasonal changes has shaped the evolution of deep sea species, creating biological calendars that operate independently of surface seasonal cues. The conservation challenges facing deep sea ecosystems reflect the disconnect between the timescales of human activity and the slow processes that govern life in the abyss. Damage to deep sea communities can persist for centuries or millennia, while recovery may be impossible within any human time frame. The slow growth rates and long lifespans of deep sea organisms mean that populations disturbed by human activities may never fully recover, creating permanent changes to ecosystems that took millions of years to develop. The exploration of deep sea environments continues to reveal the remarkable diversity and complexity of life in Earth's most remote habitats, with each new expedition uncovering species and behaviors that expand our understanding of life's possibilities. The technology required to study deep sea ecosystems pushes the boundaries of human engineering, creating tools that must operate reliably under conditions more extreme than those found on other planets. These technological challenges make deep sea exploration one of the final frontiers for human discovery on our own planet. The interconnections between deep sea and surface ecosystems create global networks of biological and chemical exchange that influence planetary processes ranging from climate regulation to nutrient cycling. The deep ocean's role as a planetary thermostat and carbon reservoir makes the health of deep sea ecosystems crucial for maintaining the environmental stability that supports all life on Earth. Understanding and protecting these deep sea systems represents one of the most important challenges facing humanity as we work to maintain the planetary systems that sustain our existence. The aesthetic beauty of deep sea environments provides inspiration and wonder that transcends scientific understanding, creating emotional connections to places most humans will never visit, but can appreciate through the images and discoveries brought back by deep sea explorers. The alien landscapes of the deep ocean remind us that our own planet contains worlds as strange and beautiful as anything we might hope to find among the stars, encouraging the kind of wonder and curiosity that drives scientific discovery and environmental protection. The future of deep-sea exploration promises to reveal even more remarkable discoveries as our technology and understanding continue to advance, opening new windows into Earth's final frontier and expanding our appreciation for the complexity and beauty of life in the abyss. Each new discovery in the deep ocean adds another thread to the tapestry of life on Earth, reminding us that the story of our planet is far from complete, and that the most amazing chapters may still be waiting to be written in the crushing darkness of the deep sea. As we drift deeper into these underwater revelations, the weight of water above seems to press gently on our consciousness, creating a sense of peaceful pressure that mirrors the experience of sinking slowly into sleep. The rhythm of deep ocean currents becomes the rhythm of breathing, slow and steady and eternal. In this vast underwater realm, where time moves like honey and life unfolds with the patience of stone, we find ourselves cradled by the same forces that have shaped our planet for billions of years. The deep ocean calls to something ancient in our consciousness, a memory of the primordial waters from which all life emerged. And in that calling, we find a peace as deep and lasting as the abyss itself. The deep sea creates its own weather systems in ways that seem to bend the laws of physics we know on land. Internal waves as tall as skyscrapers roll through the deep ocean with the slow majesty of underwater storms, their crests and troughs invisible to surface observers, yet powerful enough to move entire water masses across ocean basins. These submarine weather patterns unfold in slow motion, with individual waves taking hours to pass a single point. Their movements so gradual that deep sea creatures ride them like passengers on an infinitely patient escalator. The temperature differences that drive these internal waves are measured in fractions of degrees, yet they create currents strong enough to transport nutrients and organisms across thousands of miles of ocean floor. Deep sea creatures have learned to read these underwater weather patterns like mariners reading surface winds, timing their migrations and feeding behaviors to take advantage of the nutrient-rich waters that internal waves bring from distant regions of the ocean. The boundaries between different water masses create invisible walls in the deep ocean, barriers as distinct as mountain ranges, yet composed of nothing more than subtle differences in temperature and salinity. These underwater frontiers mark the edges of different ecosystems, with creatures on either side adapted to the specific conditions of their water mass. Crossing these boundaries can be as challenging for deep-sea organisms as crossing a desert would be for forest-dwelling animals, requiring physiological adjustments that take time and energy to accomplish. The mixing that occurs where different water masses meet creates zones of enhanced biological activity, underwater oases where nutrients from different regions combine to support communities more diverse than the surrounding waters. These mixing zones shift and pulse with the movements of the water masses themselves, creating temporary hotspots of life that appear and disappear like mirages in the deep sea desert. The salinity gradients in deep ocean water create layers as distinct as oil floating on water, each with its own community of specially adapted organisms. Some deep-sea creatures spend their entire lives within a single salinity layer, their bodies so precisely tuned to specific salt concentrations that moving up or down even a few meters would be fatal. These invisible boundaries create three-dimensional neighborhoods in the water column, with different species occupying different floors of the same underwater apartment building. The chemical signals that indicate the presence of food can persist in deep ocean water for weeks, creating scent trails that lead deep sea scavengers on journeys that span hundreds of miles. A single whale fall can broadcast its chemical signature across vast areas of ocean, drawing scavengers from distances so great that some may travel for months to reach the food source. These chemical beacons create invisible highways in the deep sea, connecting distant communities through networks of scent that operate like underwater internet systems. The magnetic fields generated by deep sea sediments create navigation aids that some creatures use to maintain their orientation in the featureless expanse of the abyss. These geological compasses provide reference points in an environment where traditional landmarks don't exist, allowing deep-sea animals to navigate with precision across underwater plains that stretch for thousands of miles without variation. The subtle magnetic signatures of different regions may serve as address systems for deep-sea creatures, helping them remember and return to productive feeding areas or suitable breeding sites. The acoustic shadows created by underwater mountain ranges and seamounts provide quiet refuges where deep-sea creatures can communicate without interference from the background noise of ocean currents and geological activity. These sound shadows create acoustic oases in the deep sea, protected spaces where the subtle communications of bioluminescent creatures can be heard clearly across greater distances than would be possible in more acoustically cluttered environments. The pressure waves generated by earthquakes and underwater landslides travel through the deep ocean like invisible tsunamis, carrying information about geological events across entire ocean basins. Deep-sea creatures may be able to sense these pressure waves long before any surface effects become apparent, using them as early warning systems for environmental changes that could affect their habitat. The ability to detect and interpret these geological communications could provide deep-sea organisms with advanced notice of changes in water temperature, current patterns, or food availability. The seasonal changes in deep-sea temperature are so subtle they're measured in hundredths of degrees. Yet these tiny variations can trigger behavioral changes in creatures that have evolved to detect the faintest environmental cues. Deep-sea organisms may time their reproductive cycles to coincide with these barely perceptible seasonal signals, ensuring that their offspring are born during periods when conditions are most favorable for survival. The precision required to detect and respond to such minute changes demonstrates the remarkable sensitivity that deep sea life has developed over millions of years of evolution. The deep ocean's role as a planetary memory system extends beyond climate records preserved in sediment cores to include the chemical signatures of ancient volcanic eruptions, meteor impacts, and mass extinction events. The water itself carries dissolved minerals and isotopes that tell the story of Earth's geological history, creating a liquid library that scientists are only beginning to learn how to read. Each sample of deep ocean water contains information about environmental conditions that existed thousands of years ago when that water last contacted the atmosphere at the surface. The circulation patterns that move water through the deep ocean create conveyor belt systems that operate on timescales longer than human civilization, carrying water masses on journeys that connect the Arctic with the Antarctic, through pathways that remain hidden beneath miles of overlying water. These circulation systems help regulate global climate by transporting heat and carbon dioxide between different regions of the planet, creating stability in Earth's environmental systems that has persisted through ice ages and warm periods alike. The pressure gradients that exist in the deepest ocean trenches create unique opportunities for chemical reactions that cannot occur anywhere else on Earth, potentially producing compounds that could revolutionize medicine and materials science. The extreme conditions in these deepest environments may serve as natural laboratories where new forms of matter and energy are created through processes that we're only beginning to understand. The exploration of these pressure-induced chemical reactions could yield discoveries that transform our understanding of chemistry and physics. The energy sources that power life in the deepest ocean trenches often come from the Earth's interior itself, with radioactive decay and geothermal heat providing the foundation for ecosystems that operate completely independently of solar energy. These geologically powered communities demonstrate that life can thrive using energy sources that exist throughout the universe, suggesting that similar ecosystems might exist on other worlds where sunlight is unavailable but internal heat sources persist. The adaptation strategies that allow creatures to survive in the deepest ocean trenches often involve partnerships with bacteria that can process toxic chemicals and convert them into useful nutrients. These symbiotic relationships create biological recycling systems that can extract energy and nutrition from chemical compounds that would be deadly to most surface-dwelling organisms. The bacteria that participate in these partnerships have evolved metabolic pathways that seem to violate the basic rules of biology as we understand them from studying surface life. The reproductive strategies of the deepest dwelling creatures often involve complex timing mechanisms that ensure eggs and sperm are released simultaneously despite the vast distances that may separate individual organisms. Some species use chemical signals that can travel for hundreds of miles through deep ocean water, coordinating reproduction across populations that are spread over areas larger than entire countries. These long-distance reproductive communications create invisible networks of genetic exchange that maintain species diversity across the largest habitat on Earth. The feeding relationships in the deepest ocean communities often involve creatures that specialize in consuming specific types of organic matter, creating recycling systems that ensure nothing edible goes to waste. Some deep-sea organisms have evolved to feed exclusively on the wooden remains of sunken ships, while others specialize in processing the chitin shells of dead crustaceans or the calcium carbonate skeletons of deep-sea corals. These specialized feeding strategies create communities where every type of organic matter finds a consumer perfectly adapted to processing it. The bioluminescent communications in the deepest ocean zones often operate on wavelengths of light that can penetrate further through high-pressure water than the blue-green light used by creatures in shallower depths. These deep red and infrared communications create invisible conversations that occur entirely outside the range of human vision, using portions of the electromagnetic spectrum that remain largely unexplored in biological systems. The discovery that deep-sea creatures can see and communicate using infrared light has opened entirely new areas of research into the sensory capabilities of deep ocean life. The territorial behaviors of creatures in the deepest ocean trenches often involve the defense of specific chemical microenvironments rather than physical locations, with individuals claiming ownership of particular water masses based on their chemical composition rather than their geographic coordinates. These chemical territories can move and shift with current patterns, creating property boundaries that exist in 4 dimensions and change constantly with the flow of deep ocean water. The ability to track and defend these mobile territories requires sensory capabilities and cognitive skills that rival those of the most intelligent surface-dwelling animals. The migration patterns of deep trench creatures often involve vertical movements that span the entire water column, with some species traveling from the deepest ocean floors to the twilight zone and back again in journeys that take months to complete. These vertical migrations allow deep-sea organisms to exploit food resources that exist at different depths, creating connections between communities separated by miles of water. The energy required for these massive vertical migrations is enormous, yet the nutritional benefits gained from accessing different feeding zones make the journey worthwhile. The social structures that develop in deep ocean communities often persist across multiple generations. With knowledge about feeding areas, migration routes, and predator avoidance strategies passed down through learned behaviors that are transmitted from parents to offspring over periods spanning decades. These cultural traditions in deep-sea communities create continuity that helps species adapt to environmental changes and maintain successful survival strategies across centuries of changing ocean conditions. The camouflage strategies used by the deepest dwelling creatures often involve the manipulation of bioluminescent patterns to match the specific light conditions of their environment, creating adaptive camouflage systems that can change in real time to match changing background illumination. Some deep-sea creatures can adjust their bioluminescence to match the light signatures of different species, creating mimicry systems that allow them to blend in with schools of other organisms or impersonate more dangerous species to avoid predation. The symbiotic relationships between deep-sea creatures and their bacterial partners often involve the exchange of genetic material that allows both species to adapt more quickly to changing environmental conditions. These genetic partnerships create hybrid systems that combine the adaptive capabilities of both bacteria and their hosts, resulting in organisms that can respond to environmental challenges with flexibility that would be impossible for either species alone. The discovery that genetic exchange between species is common in deep-sea environments has revolutionized our understanding of how evolution operates in extreme environments. The sensory capabilities of deep ocean creatures often extend far beyond the five senses familiar to surface dwellers, with many species able to detect electric fields, magnetic variations, and chemical gradients with precision that surpasses the most sensitive scientific instruments. These enhanced sensory systems allow deep-sea creatures to navigate and hunt in environments where traditional senses would be useless, creating perception systems that seem almost supernatural in their sensitivity and accuracy. The communication networks that connect deep-sea communities often operate through combinations of chemical signals, bioluminescent displays, and low-frequency vibrations that can travel for hundreds of miles through deep ocean water. These multimodal communication systems create information networks that span entire ocean basins, allowing deep-sea creatures to coordinate behaviors and share information about environmental conditions across distances that would make other forms of communication impossible. The reproductive cycles of many deep-sea species are synchronized with environmental cues that may originate thousands of miles away, with creatures timing their breeding to coincide with seasonal changes in water temperature or current patterns that affect food availability months later. These long-range environmental forecasting abilities allow deep-sea organisms to prepare for future conditions based on subtle signals that may barely be detectable, but contain crucial information about coming changes in ocean conditions. The feeding strategies of deep-sea filter feeders often involve the creation of elaborate filtration systems that can extract nutrition from water that appears completely barren to human observation. These biological filters can concentrate nutrients from enormous volumes of water, creating food-gathering systems that operate continuously and efficiently in environments where food particles may be separated by cubic meters of apparently empty water. The efficiency of these biological filtration systems surpasses anything achieved by human technology designed for similar purposes. The waste processing systems that operate in deep-sea communities create closed-loop recycling networks where nothing organic goes unused. With specialized organisms filling every possible ecological niche, from primary decomposers to secondary recyclers that process the waste products of other decomposers. These complete recycling systems ensure that the limited organic matter that reaches the deep sea is utilized with maximum efficiency, creating sustainable communities that have operated without external inputs for millions of years. The defensive strategies employed by deep-sea creatures often involve the production of chemical compounds that are toxic to predators but harmless to other species in their community, creating chemical neighborhood systems where compatible species can coexist safely while dangerous predators are deterred by the presence of defensive chemicals. These chemical defense networks create safe zones in the deep sea where vulnerable species can find refuge from predation, while maintaining access to feeding and breeding areas. The exploration of deep-sea environments continues to reveal new forms of life that challenge our understanding of what conditions can support living organisms. With recent discoveries, including creatures that thrive in water so acidic it would dissolve metal, temperatures hot enough to melt lead, and pressures that would crush diamonds. These extreme environment specialists demonstrate that life's boundaries are far broader than we previously imagined, expanding the range of conditions where we might expect to find living organisms both on Earth and on other worlds. The technological challenges involved in studying deep-sea life require the development of equipment that can operate reliably under conditions more extreme than those found in outer space, creating engineering problems that push the limits of materials, science, and mechanical design. The solutions developed for deep-sea exploration often find applications in other extreme environments, contributing to advances in space exploration, high-pressure manufacturing, and materials that must operate under extreme conditions. The conservation of deep-sea ecosystems faces unique challenges due to the remoteness and inaccessibility of these environments, making it difficult to monitor changes or assess the impact of human activities on deep-sea communities. The slow reproduction rates and long lifespans of deep-sea organisms mean that damage to these ecosystems may be effectively permanent on human timescales, making prevention of harm far more important than restoration efforts that may take centuries to show results. The economic value of deep-sea resources creates conflicts between conservation efforts and extraction industries that seek to harvest minerals, energy sources, and biological products from deep ocean environments. The resolution of these conflicts requires international cooperation and long-term thinking that considers the value of intact deep-sea ecosystems alongside the immediate economic benefits of resource extraction, creating policy challenges that span multiple countries and generations. The climate regulation services provided by deep-sea ecosystems represent one of their most important contributions to planetary stability, with deep ocean communities playing crucial roles in carbon sequestration, heat distribution, and the maintenance of ocean chemistry that supports life throughout the marine environment. The economic value of these ecosystem services far exceeds the value of most extractable resources. Yet these services are often overlooked in economic calculations because they don't generate immediate financial returns. The educational value of deep-sea exploration extends far beyond scientific research to include inspiration and wonder that encourage young people to pursue careers in science, technology, and environmental protection. The alien beauty of deep-sea creatures and environments captures imaginations in ways that more familiar ecosystems cannot, creating emotional connections that motivate long-term commitment to understanding and protecting the natural world. The philosophical implications of deep-sea discoveries challenge human-centered views of life and intelligence, revealing forms of consciousness and communication that operate according to principles very different from those familiar to terrestrial life. The study of deep-sea intelligence and social organization provides insights into alternative forms of consciousness that may exist elsewhere in the universe, expanding our understanding of what intelligence might look like under different environmental conditions. The spiritual significance of the deep ocean as Earth's final frontier provides a source of humility and wonder that connects us to the larger systems that sustain all life on our planet. The realization that vast areas of our own world remain unexplored and mysterious offers a counterbalance to the technological confidence of modern civilization, reminding us that mystery and discovery remain fundamental aspects of human experience, even in an age of rapid scientific advancement. As we float here in the embrace of these deep ocean mysteries, feeling the gentle pressure of water and time pressing down around us, the boundary between wakefulness and sleep becomes as fluid as the currents themselves. The rhythm of our breathing synchronizes with the slow pulse of deep ocean tides, and our consciousness drifts like marine snow through layers of awareness, each one deeper and more peaceful than the last. In this underwater meditation, where every fact becomes a gentle current and every discovery a soft landing on the sea floor of sleep, we find ourselves cradled by the same ancient waters that gave birth to all life on Earth, carried gently toward dreams as vast and mysterious as the abyss itself. The deep ocean holds memories in ways that seem to transcend the physical world, creating archives of experience that span geological ages. In the deepest sediment layers, microscopic shells and fragments tell stories of ancient climates, preserving the chemical signatures of ice ages that ended before humans walked the Earth. These tiny time capsules drift down through millennia, each one carrying information about the world that existed when it was formed, creating libraries written in calcium and silica that scientists can read like pages from Earth's autobiography. The creatures that inhabit these sediment archives often live their entire lives surrounded by the compressed history of their planet, crawling across surfaces that contain the fossilized remains of organisms that lived millions of years ago. Deep sea worms tunnel through layers of time itself, their burrows connecting different epochs as they move between sediment layers that were deposited during different periods of Earth's history. These living archaeologists process the remains of ancient life forms, recycling nutrients that have been locked away in the sediment for eons and making them available to contemporary deep-sea communities. The chemical gradients that exist within deep-sea sediments create opportunities for unique metabolic processes that can extract energy from compounds that have been buried for thousands of years. Bacteria living deep within the sediment layers can metabolize organic matter that was deposited when the climate was completely different from today's conditions, creating energy cycles that connect the present with the distant past. These sediment-dwelling communities operate on such slow metabolic rates that individual bacteria may live for centuries, their cellular processes unfolding with the patience of geological time. The water that fills the spaces between sediment grains often contains dissolved minerals and organic compounds that originated from sources thousands of miles away and hundreds of years in the past, creating chemical time capsules that preserve the signatures of long-vanished environmental conditions. This interstitial water moves so slowly through the sediment that it can take decades to travel distances measured in inches, creating transport systems that operate according to their own temporal logic, independent of the faster rhythms that govern life in the water column above. The bioturbation created by sediment-dwelling creatures produces patterns in the seafloor that can persist for decades, creating landscapes of small mounds and depressions that serve as microhabitats for other deep-sea organisms. These biogenic structures modify the flow of bottom currents and create areas of enhanced mixing that can concentrate nutrients and provide shelter for creatures that require specific environmental conditions. The architects of these underwater landscapes work with the patience of master gardeners, slowly sculpting their environment over periods that span multiple human generations. The acoustic properties of deep-sea sediments create unique sound environments where vibrations can travel for great distances through the solid substrate, potentially allowing sediment-dwelling creatures to communicate across areas much larger than they could reach through chemical or bioluminescent signals. These substrate-borne communications may operate at frequencies too low for humans to detect, creating underground telephone systems that connect communities separated by miles of seafloor. The ability to send and receive these vibrational messages could provide sediment-dwelling organisms with information about food sources, predators, and potential mates across vast areas of the deep sea floor. The magnetic properties of sediment layers create navigation aids that may help deep sea creatures orient themselves relative to Earth's magnetic field, providing compass references in environments where other directional cues are absent. The iron-rich minerals embedded in deep-sea sediments record the orientation of Earth's magnetic field at the time they were deposited, creating magnetic maps that reflect the planet's geomagnetic history. Creatures sensitive to magnetic fields could potentially use these geological compasses to maintain their orientation during long-distance migrations across the apparently featureless abyssal plains. The temperature variations within deep-sea sediments are so subtle that they're measured in thousands of degrees, yet these tiny thermal differences may provide important environmental cues for creatures that have evolved to detect the faintest signals. The heat that rises from Earth's interior creates thermal gradients within the sediment that can indicate the presence of geological activity, chemical processes, or the proximity of other organisms. These thermal landscapes exist in dimensions too small for human perception, but may represent highways of information for creatures adapted to navigate by temperature. The chemical weathering processes that occur within deep sea sediments create ongoing transformations of mineral composition that can alter the chemical environment over periods of years or decades. These slow chemical reactions produce new compounds and release stored elements back into the water column, creating nutrient pulses that can support bursts of biological activity in overlying communities. The sediment acts as a slow-release fertilizer system, gradually providing essential nutrients to deep-sea ecosystems through processes that operate continuously over geological timescales. The microbial communities that inhabit deep-sea sediments create complex ecosystems that may contain more species diversity than any other environment on Earth, with countless varieties of bacteria and archaea filling every possible ecological niche within the sediment matrix. These microscopic communities process organic matter through intricate food webs that involve dozens of different metabolic pathways, creating recycling systems that can extract energy and nutrients from virtually any organic compound that reaches the sea floor. The diversity and complexity of these sediment ecosystems rivals that of tropical rainforests, yet operates in complete darkness and at crushing pressures that would be instantly fatal to surface-dwelling organisms. The fossilization processes that occur in deep-sea sediments preserve not only the hard parts of organisms, but also delicate soft tissues and even cellular structures, creating fossil records of exceptional quality that provide detailed insights into the evolution and ecology of ancient deep-sea communities. The low oxygen conditions and stable chemistry of deep-sea sediments create ideal conditions for preservation, resulting in fossils that retain details of anatomy and behavior that are rarely preserved in other environments. These exceptional fossils provide windows into deep-sea ecosystems that existed millions of years ago, revealing how these communities have changed and evolved over geological time. The fluid dynamics of water movement through deep-sea sediments create complex flow patterns that can concentrate nutrients in specific areas while depleting others, creating patchy distributions of resources that influence the distribution and behavior of sediment-dwelling organisms. These subsurface current systems operate according to principles of groundwater flow, with water moving through the sediment matrix in response to pressure gradients, chemical differences, and gravitational forces. The resulting flow patterns create underground river systems that can transport nutrients, organisms, and chemical signals across large areas of the sea floor. The seasonal variations in the rate of organic matter deposition create annual rhythms in deep-sea sediments, with layers of enhanced organic content marking periods when surface productivity was higher and more marine snow reached the sea floor. These seasonal signatures can be read in sediment cores like tree rings, providing records of ocean productivity that extend back thousands of years. The creatures that live within these sediments may be able to detect these seasonal variations and time their reproductive cycles or feeding behaviors to coincide with periods of enhanced food availability. The compression forces that act on deep-sea sediments create unique physical environments where the normal rules of fluid dynamics and mass transport are modified by the extreme pressures involved. Water and dissolved substances move through compressed sediments according to principles that differ significantly from those governing transport in surface environments, creating opportunities for chemical and biological processes that cannot occur anywhere else on Earth. These pressure-modified environments may serve as natural laboratories for studying how life and chemistry operate under conditions similar to those that exist deep within planetary interiors. The electrical properties of deep-sea sediments create weak but detectable electrical fields that may serve as navigation aids or communication channels for creatures equipped with appropriate sensory organs. The chemical reactions occurring within the sediment matrix generate small electrical currents that could be sensed by organisms with electroreceptive capabilities. potentially providing information about chemical gradients, biological activity, or geological processes occurring within the sediment. These bioelectrical phenomena create invisible landscapes of electrical activity that may be as important to sediment-dwelling creatures as visual landscapes are to surface-dwelling animals. The deep ocean's twilight zone experiences migrations that dwarf any movement of life on land. Yet these massive journeys unfold with such regularity that they create predictable rhythms in the water column. Every evening, as darkness falls on the surface far above, billions of creatures begin their ascent from the depths, rising hundreds of meters through the water column in search of food in the more productive upper waters. This daily vertical migration involves more biomass than any other regular movement of animals on Earth, creating a living escalator that operates continuously between the deep ocean and the surface waters. The creatures that participate in this migration have evolved remarkable adaptations for surviving the pressure changes involved in traveling such vast vertical distances on a daily basis. Their swim bladders can adjust rapidly to accommodate the changing pressure, while their bodies are designed to handle the physiological stress of moving between environments with dramatically different pressure, temperature, and chemical conditions. These daily commuters of the deep sea demonstrate biological engineering solutions that allow them to exploit resources across multiple ocean zones while maintaining their physiological integrity throughout their vertical journeys. The timing of these migrations is synchronized with extraordinary precision, creating waves of ascending and descending life that move through the water column like slow-motion tsunamis of biology. The creatures involved in these migrations use a combination of internal biological clocks and environmental cues to coordinate their movements, ensuring that they arrive at their destination zones at optimal times for feeding while minimizing their exposure to predators. This coordination creates traffic patterns in the ocean that operate with the reliability of commuter trains, moving predictable populations of organisms between different ocean zones on schedules that have remained stable for thousands of years. The ecological connections created by these migrations link surface and deep ocean ecosystems in ways that make them functionally inseparable, with nutrients and energy flowing between zones through the bodies of migrating creatures. The animals that feed in surface waters at night carry that nutrition back to the deep ocean during the day, transporting carbon and other essential elements from the productive surface zones to the nutrient-poor depths. This biological conveyor belt helps maintain the productivity of deep ocean ecosystems by providing a constant flow of resources from the surface world above. The predatory relationships that develop around these migration routes create dynamic hunting grounds where deep-sea predators position themselves to intercept migrating prey at predictable times and locations. These ambush predators have evolved strategies that take advantage of the regular timing and routes of the migrants, creating underwater versions of the predator-prey relationships that develop around terrestrial migration routes. The deep-sea equivalent of lions waiting at river crossings involves creatures with bioluminescent lures and expandable jaws positioning themselves along migration highways to capture unwary travelers. The communication systems that coordinate these migrations often involve bioluminescent displays that can be seen for great distances through the clear, deep ocean water, creating light shows that serve both as navigation aids and social coordination signals. Different species use distinct patterns of flashes and glows to identify themselves and maintain group cohesion during their vertical journeys, creating a form of underwater air traffic control that prevents collisions and ensures that each species reaches its optimal feeding depth. These bioluminescent communications create moving constellations in the water column, with patterns of light that shift and flow as different groups of migrants pass through the same areas. The physiological challenges of these daily migrations require remarkable metabolic flexibility, with migrating creatures adjusting their internal chemistry to handle the changing conditions they encounter during their vertical travels. The temperature differences between deep and shallow waters can span dozens of degrees, while the pressure changes involved in these migrations would be fatal to most surface-dwelling organisms. The creatures that make these journeys have evolved biochemical systems that can function efficiently across these extreme environmental gradients, creating metabolic machinery that operates effectively under conditions that change dramatically twice each day. The navigation systems that guide these migrations operate in three-dimensional space, with creatures using combinations of pressure sensitivity, magnetic field detection, and chemical gradient following to maintain their course during journeys that may last several hours each way. These navigation systems must account for ocean currents that can carry migrants off course, predator avoidance behaviors that require detours from optimal routes, and the need to arrive at specific depths at optimal times for feeding. The precision required for these navigation tasks rivals that of any human navigation system, yet operates entirely through biological processes that have been perfected over millions of years of evolution. The energy budgets involved in these migrations represent major investments for the creatures that undertake them, with some species expending up to half of their daily energy intake on the journey itself. This enormous energy cost is justified by the access to food resources that would otherwise be unavailable, creating cost-benefit calculations that favor migration despite the metabolic expense involved. The evolution of these migration patterns reflects the fundamental truth that in the resource-limited deep ocean, access to additional food sources can make the difference between survival and starvation. The seasonal variations in these migration patterns reflect changes in surface ocean productivity, with the intensity and timing of migrations adjusting to match the availability of food in surface waters. During periods of high surface productivity, more creatures participate in the migrations, and they may travel greater distances to take advantage of the enhanced feeding opportunities. These seasonal adjustments create dynamic relationships between surface and deep ocean ecosystems, with the health and productivity of each zone influencing the other through the medium of migrating organisms. The deep ocean's hydrothermal vents create underwater cities that operate according to principles completely different from any surface ecosystem, powered by chemical energy rising from Earth's interior rather than sunlight falling from above. These submarine metropolises cluster around volcanic vents where superheated water, rich in dissolved minerals, erupts from cracks in the sea floor, creating oases of abundance in the otherwise sparse, deep ocean environment. The energy that powers these communities comes from chemosynthetic bacteria that convert toxic chemicals into organic compounds, forming the foundation of food webs that support some of the most remarkable creatures on Earth. The architecture of these vent communities reflects the unique challenges of life around underwater volcanoes, where temperatures can vary from near 0 degrees Celsius to over 100 degrees Celsius, boiling to near freezing within the space of inches. The creatures that colonize these environments have evolved specialized adaptations that allow them to thrive in the narrow zones where conditions are suitable for life. creating communities that exist in delicate balance between the scorching heat of the vents and the frigid cold of the surrounding deep ocean. These biological engineers create structures that modify their local environment, building reef-like formations that provide shelter and create microhabitats within the larger vent ecosystem. The succession patterns in vent communities follow predictable sequences as new vents open and mature vents cool and close, creating temporal landscapes where different species dominate at different stages of a vent's life cycle. Pioneer species are the first to colonize new vents, followed by more specialized creatures that require the stable conditions that develop as vent communities mature. This ecological succession creates a dynamic mosaic of communities at different stages of development, with young vents supporting different species assemblages than older, more established systems. The chemical gradients that surround hydrothermal vents create complex three-dimensional habitat structures where different species occupy specific zones based on their tolerance for temperature, chemical composition, and toxic compounds. These chemical zonation patterns create distinct neighborhoods within vent communities, with each zone supporting its own characteristic fauna adapted to the particular conditions found at that distance from the vent opening. The result is a highly structured community where spatial organization reflects physiological capabilities and competitive relationships. The symbiotic relationships that dominate vent ecosystems create biological partnerships that seem to blur the boundaries between different organisms, with many vent species depending entirely on bacterial symbionts for their nutrition and energy needs. These partnerships have evolved to such intimate levels that host and symbiont function as integrated biological systems, sharing metabolic processes and cellular machinery in ways that create organisms that are neither purely animal nor purely bacterial, but something entirely new. The evolution of these symbiotic relationships represents one of the most remarkable examples of biological cooperation found anywhere on Earth. And so our journey through the deepest, most peaceful corners of our planet draws to a close. We've drifted through bioluminescent gardens where living light paints the darkness, witnessed the gentle snowfall of marine nutrients that feeds entire ecosystems, and explored the crushing depths where life creates beauty from impossibility itself. Each discovery has carried us deeper into wonder, revealing that even in Earth's most remote places, mystery and majesty flow together like ancient currents. As you let these ocean secrets settle into your consciousness like sediment on the abyssal plains, may you find the same peace that exists in those timeless depths, where patience is wisdom and every breath moves to the rhythm of tides that have pulsed since the beginning of time. Sleep well and dream of waters deeper than starlight,